Welcome to this tutorial on determinants, Cramer's rule, and linear transformations. These three concepts form the foundation of linear algebra and have numerous applications in mathematics, physics, computer science, and engineering. Let's start by understanding determinants. The determinant is a special number associated with a square matrix that tells us important properties about the matrix. For a 2 by 2 matrix, the determinant is calculated as a times D minus B times C. This is sometimes remembered as the product of the main diagonal minus the product of the other diagonal. For a 3 by 3 matrix, the calculation is more complex. The determinant can be calculated using a method called cofactor expansion. We multiply each element in the first row by its cofactor and sum them up with alternating signs. Let's try an example to make this clear. Now that we know how to calculate determinants, let's explore their key properties. First, determinants are multilinear. This means if you scale one row by a constant k, the determinant scales by the same factor k. Second, if you add a multiple of one row to another row, the determinant remains unchanged. Third, swapping two rows changes the sign of the determinant. Fourth, the determinant of a product of matrices equals the product of their determinants. One of the most important properties of determinants is their relationship to matrix invertibility. A matrix is invertible if and only if its determinant is non-zero. If the determinant is 0, we call the matrix singular, meaning it's not invertible. This has important implications for solving systems of linear equations. A system with a non-zero determinant has a unique solution, while a system with a zero determinant either has no solution or infinitely many solutions. Now, let's look at the geometric interpretation of determinants. The determinant tells us how a linear transformation affects area or volume. In 2 dimensions, the absolute value of the determinant gives the factor by which areas are scaled. The sign of the determinant indicates whether the transformation preserves or reverses orientation. For example, in 2D, if we start with a unit square and apply a transformation with determinant 2, the resulting parallelogram will have an area of 2 square units. Now, let's move on to Cramer's rule, which is a method for solving systems of linear equations using determinants. For a system of n linear equations in n unknowns represented as ax equals b, Cramer's rule gives us a direct formula for each variable. For each variable x sub j, we calculate the ratio of 2 determinants. The determinant of a modified matrix, a sub j, divided by the determinant of the original matrix, A. The modified matrix, A sub j, is formed by replacing the jth column of A with the vector B. Let's solve a 2 by 2 system using Cramer's rule. Consider the system: 3x plus 2y equals 7 and x minus y equals 1. First, we write this in matrix form with coefficient matrix A, variable vector x, and constant vector b. Next, we calculate the determinant of A, which is 3 times negative 1 minus 2 times 1, which equals negative 5. Then, we create an underscore 1 by replacing the first column of A with B. Its determinant is 7 times negative 1 minus 2 times 1, which equals negative 9. Similarly, we create an underscore 2 by replacing the second column with B. Its determinant is 3 times 1 minus 7 times 1, which equals negative 4. Finally, using Cramer's rule, x equals det A underscore 1 over det A, which is negative 9 over negative 5, or 1.8, and y equals det A underscore 2 over det A, which is negative 4 over negative 5, or 0.8. Now, let's explore linear transformations, which are represented by matrices. A linear transformation is a function that preserves vector addition and scalar multiplication. Every linear transformation from r to the power of n to r to the power of m can be represented by an m by n matrix. Some common examples of linear transformations include rotations, reflections, scaling, shearing, and projections. Let's visualize some 2D linear transformations. To summarize what we've learned, determinants are special numbers that tell us important properties about matrices. They help us determine if a matrix is invertible, and they measure how linear transformations scale areas and volumes. Cramer's rule gives us a formula to solve systems of linear equations using determinants. Linear transformations are functions that can be represented by matrices, and their geometric effects are related to the determinants of those matrices. Thank you for watching this tutorial on determinants, Cramer's rule, and linear transformations.